Organic chemistry.
So for this reaction, when you add HBr across an alkene, it follows Markov-Nikov's rule. So in this rule, it states that we're going to add the hydrogen from HBr to the side of the alkene with more hydrogens. So this means that if we were to number each side of the alkene, so let's say C1 and C2, and also what we can do is draw in those hydrogens. That means when we add this hydrogen in green across the pi bond, it's going to want to add to the side of the alkene that already has more hydrogens. So in this case, C1, the rich get richer. So when we draw out our arrows, alkene, the middle of the pi bond is going to grab that hydrogen, and then the bond will form a new lone pair on bromine. So the intermediate that we form shows that the green hydrogen from HBr will add to the C1 position. And this means that the other side of the alkene on C2 is where our carbocation is going to form. So this follows Markov-Nikov's rule. And now the second step of this reaction is that Br minus that's just floating around is going to attack the carbocation. And from here, we form our final product. So when we use H3O+, this also follows Markov-Nikov's rule. So we're going to take a look at which side of the alkene has more H's. So we can draw in the hydrogens at the C1 position, and then C2 has 0 hydrogens connected to it. So between each side of the alkene, C1 has more H's, which means H3, the hydrogen from H3O+ will add to the C1 position. And I'm just going to redraw the alkene here, just for more space, as well as the structure of H3O+. So the arrow that we're going to draw starts from the middle of the pi bond of the alkene, and it's going to grab one of the hydrogens, and the bond will form a lone pair on oxygen. So because the hydrogen from H3O+ went to the C1 carbon, that means on C2, that's where our carbocation will form. And then water, the remaining part of H3O+ comes in, and it's going to just attack the carbocation. And I'm not going to draw the extra hydrogens anymore, just the bond line structure, just for clarity. But I will draw the hydrogens connected to water. So now that the whole water molecule attached to the carbocation carbon, what we're going to do is we're going to bring in another mole of water, and it's going to deprotonate one of the extra hydrogens, just so our final product will be an overall neutral molecule. And from here, we get the final product. And note that this is a racemic mixture, just because the water molecule from this step can attack either the front or the back of the carbocation, which is why this is a racemic mixture, which you can just draw in this way, making sure that you label that this is racemic. So in this example, I'm just going to redraw the alkene down here, just so we have some more space to draw out our mechanism. And I'm also going to draw out the bonds in between the two bromine atoms. So the first step of this reaction starts from the middle of the pi bond, and it goes towards one of the bromines of Br2. second arrow, and if you want, you can even draw in the lone pairs on bromine if that helps you visualize what's happening more. And then the second arrow is that one of the lone pairs of bromine is going to attack one of the carbons of the alkene, and then the second bromine is going to break off, so this bond will just form a lone pair of electrons onto Br. And what this forms is a bromonium ion. So it's basically a 3-membered ring with bromine at the tip of the triangle. And this bromine, or bromonium ion is what they call it, has a plus charge on Br, and the 2 bonds that connect Br to the 2 carbons on this ring for this particular example can either add as both wedges or both dashes. So Br2 adds across the alkene via syn addition. And if in this case, if we draw it as both wedges, that means this extra methyl group that's hanging out here will just be drawn on a dashed bond like this. And then in this particular reaction, because we're using water, which is a protic solvent, that means that we're going to have the water attack the bromonium ion at the more substituted position. So if we were to label this as C1 and C2, C1 is more substituted because the C1 carbon is connected to 2 other carbons, whereas C2 is only connected to 1 carbon. So water is going to want to attack the more substituted spot. So when it attacks C1, the bromonium ion is going to open up. So this wedged bond is going to form a new lone pair on Br. And when water attacks C1, it will attach as the opposite bond type of the bromonium ion. So because Br is currently drawn as wedged bonds, when water attaches to C1, it will attach as a dashed bond. And if water is attaching as a dashed bond, that means this methyl group will be on a wedge. But Br will maintain its stereochemistry on a wedged bond like this. And now what's going to happen, because we have this whole water molecule that attached, we want to make our product overall neutral. So this leftover Br minus from Br2 that's just floating around is going to come back and it will deprotonate the extra hydrogen from water to form a new lone pair on oxygen, and from here we'll get our final product. Where in this case, the bromine group, as well as the alcohol group, added via anti-addition, just because you'll see that the alcohol is on a dashed bond and the bromine is on a wedged bond. And this also forms its enantiomer as well. All right, so for this example, we can see that the alcohol group added to the less substituted side of the alkene. How do we know that? What you can do is that we can label each side of the alkene and see at which carbon did the alcohol in the product place onto. So if we look at the starting alkene, let's label this as C1 and this as C2. And we can even draw in any hydrogens that are missing if that helps you identify which side is more or less substituted. Because none of the carbon arrangements changed from the reactant to the product, that means we can still label our carbons as the same numbers, C1 and C2. So we notice that the alcohol group added to the C2 position. This tells us that the alcohol added to the less substituted side of the alkene. So if OH adds to the less substituted side of the alkene, that means that this is following anti-Markovnikov's rule. What that means is the only reagent that you guys know that follows anti-Markovnikov's rule is hydroboration oxidation. BH3THF as step 1, step 2, H2O2, NaOH, and water. So for this example, we're also predicting what reactant would form in the product. And in this case, if we were to label each side of the alkene again, so this is C1, that's C2, 1 and 2, because the alcohol added to the more substituted side of the alkene, in this case C1, this means that this follows Markovnikov's rule. And in order for us to choose a reagent that follows Markovnikov's rule without wanting to form any side reactants or side products from carbocation rearrangements, the only reagent that you can use that forms alcohols at the more substituted position without carbocation rearrangement is using oxymercuration demercuration, where the first step we can use HgOAC2 and water. Second step, you can use sodium borohydride or NaBH4 in order to complete this product. So for this reaction, we cannot use oxymercuration demercuration or hydroboration oxidation for this particular reaction, because if we take a look at the reactants and the products, we can see that the alcohol group added to a different carbon from where the alkene carbons started from. If you want a more visual analysis of this, if we were to number the carbon chain going from 1 through 5, and then do the same thing in the products, you'll see that the alkene carbons were originally on C1, C2. And if this were to follow either of the two reactions we just mentioned, oxymercuration or even hydroboration, that would mean the alcohol would have to add to either C1 or C2. But in this case, we added it to C3. So in order for this to happen, that means some sort of carbocation rearrangement occurred. We don't know which type yet, but we do know it did happen. So the only reaction that you can use that adds an alcohol group that does have the ability to have a carbocation rearrangement was if we used H3O+. So let's go through the mechanism of that. So I'm going to draw out the structure of H3O+. And then the first step, the alkene, is going to grab one of the hydrogens, and then the bond will form a lone pair on O. This follows Markovnikov's rule. So if we were to take a look at the carbons, C1 versus C2, C1 has 2 H's, C2 has 1 H. The H of H3O+ will want to go to the side with more H's. So in this case, it'll go to C1, which means the carbocation should go on to the C2 position. So now if we take a look at the product that they want us to form, you'll note that the methyl group on C3 is still in the product, which means we're not going to do a methyl shift or an alkyl shift, just because all of the carbons from reactant to product stayed the same. So because of that, we're going to perform a hydride shift instead. And because we want the carbocation to move to C3, we're going to move the hydrogen from the C3 position. So your arrow is going to go from the bond between the H and C3, and it's just going to go to the C2 position. Then from here, we form a new, more stable tertiary carbocation where water can attack to. So because water currently has an extra hydrogen, we're going to have another mole of water come in and deprotonate. And then from here, we get the product. So for this reaction, the first step uses NaOH and DMSO, and we currently have a secondary alkyl halide. So this means that we're going to perform an E2 mechanism. Now we have to look at the size of the base. OH is small, so that means we're going to look at using Zaitsev's rule. So I'm just going to redraw our substrate here. So between the two beta carbons, if this is our alpha position, we have beta 1, beta 2. Beta 1 has less H's than beta 3. So we're going to want to deprotonate a hydrogen from the beta 1 position because that follows Zaitsev's rule. So our OH minus is going to come in, deprotonate that H, form a double bond in between the alpha and beta carbons, and then chlorine's going to pop off. So now we get this product after the first step, and now we're going to react it with H3O+, which I won't draw the mechanism for just because you've seen it a couple times already. But because this follows Markov-Nikov's rule, the hydrogen will add to the side of the alkene with more H's, which means the alcohol will add to this carbon here. And again, this forms a racemic mixture.